Hey everyone, welcome back to Data Mining and Predictive Analytics. I'm Dr. Bolton, and today we're going to talk about our second textbook in this course, Data Mining and Predictive Analytics, written by Daniel LaRose and his daughter Chantel. We're specifically going to look at Chapter 2, which is titled Data Pre-Processing, and in here we're going to discuss all of the different ways that we need to be able to handle our data prior to being able to do more of that advanced modeling. So why do we actually need to do data pre-processing? Well, oftentimes the data that we're going to get as data analysts, as data scientists, is going to be raw data that's often incomplete and noisy. As biomedical informatics, someone who deals a lot with healthcare records, I can tell you this is more often than not the case when dealing with medical data. Oftentimes, data is going to come to you with obsolete fields, missing values, outliers, data that may not be suitable for any kind of data mining purposes, or have a bunch of errors in them as well. For data mining, this is what we call pre-processing. And this is when we take our data and do the data cleaning that it needs. All right, we're going to talk about all of that and doing any kind of data transformation. In fact, most of the time that we spend as data analysts and data scientists, over 60% of that effort is spent doing data pre-processing and data prep, getting it ready for the modeling, getting ready for the statistical analysis, beating these things into submissions so that we can actually work with them. All right, and a lot of the times we've talked a lot about databases earlier in this course, and so oftentimes the legacy databases that we're dealing with may have not been looked at for years. They may be expired, no longer relevant, and missing all kinds of data. And so the idea is that you have garbage in, you get garbage out, right? And so if we're doing pre-processing, the idea is to try to minimize the amount of garbage that we input into our models, input into our statistical analysis. Then the results from those analyses should be, much, much better as well. All right, so let's take a little short, take a look at this short little data set that we have where I've got like 7 different variables here: customer ID, zip code, gender, income, age, marital status, and transaction amount. At just quick glance at this, it probably looks like a perfectly legit data set. Looks like there's a missing value in gender, all right, but everything else looks okay. But if we look at this data set a little bit more closely, we'll see that even, at each column level, at each variable level, there are problems. Take, for instance, the zip code. Inside this small data set, not all the zip codes are formatted the same. In the US, we use a 5-digit zip code, all numerical, but other countries use different alphanumeric codes, and they may not even have 5 digits in them, all right? And so we can't assume, especially if it's an international data set, that the data sets that we're working with are formatted for US, all right? And so understanding that you're going to get some unusual values in some fields is important when you're analyzing it. All right, and so if we look at the other income fields like income, all right, we see an income field of 10 million. All right, is that assumed a gross annual income, considering that all the other values are kind of similar in size? We also have a negative value. All right, is that an extreme value? Why would somebody have a negative income? And then we also see that all the income fields are kind of close to rounded up to 50,000, 40,000, 75,000. Why is there a 99999, right? And so these are the kind of things that we need to be careful with and examining these values to make sure they're valid, all right, and haven't been entered in incorrectly, all right. When we look at the age field, all right, we have some different ages here. A C. Why would somebody be aged C? All right, does that mean something to the person who did the data entry, or should all of these have actual numeric fields? So should these be limited to just being numeric fields? There shouldn't be any kind of string or a character inside these fields. Also, an age field that contains a 0 should be kind of a sign right there that maybe something is off. Maybe we shouldn't have 0 values. Oftentimes with age, as a note here, they can be derived. So if we were to enter in the date of birth, all right, and then derive the age, that might be a better way of actually calculating the age category. All right. Marital status is another problematic one here. We see MWSSD. All right, married. What does M stand for? What does W stand for? What does S stand for? M might be married. W might be widow. But what about S? Does that mean single or does it mean separated? And so for all of these different categories and different entry fields, we need to maybe be aware that we might need to go discuss, hopefully with somebody who worked on this database and discuss with them any abnormalities, okay? So as we see in this database also, or in this small little data set, we saw some missing values within gender. So how do we handle missing values? Missing values can really be problematic when we're doing the data analytical methods. In fact, as you'll see later on, a lot of the methods and modeling that we do with our data won't allow you to have missing values. However, it is very common in a database that contains a large number of fields to have missing values, all right? And the absence of that information is rarely any kind of benefit to the task of the analysis that we're doing. And so we need to be careful on how we handle that. And I always say having more data is always better for the analysis, all right? And so there are a couple of different ways that we can actually handle missing values. One is to just delete the entire record altogether. All right. So if I have an observation, a row in my data set that is missing a value, all right, I might say, okay, I'm going to delete that entire record altogether, that entire row. It's not necessarily the best approach. Oftentimes, patterns of missing values in the data set, especially medical record data sets, may be what you might be actually analyzing. And then deleting records might actually introduce some biased subset. So instead of getting the full set of data, we're actually now narrowing down our data set into smaller and smaller sub data sets. And there might be valuable information in those other fields. So if I delete the entire row or entire instance of a observation, I'm not only deleting the missing data that I have, but I'm also now deleting that other valuable information that might be able to go into my analysis. All right. So there are three alternative methods as well that you might consider. One is replacing missing values with a user constant. So if I look at the table down here, so for categorical variables, I might try to replace that with just the word missing so that I actually know that there are missing values instead of like NA or NaN or whatever it is. Actually replacing it with the word missing will allow me to actually understand that those are missing values. All right. For continuous variables, I might think to replace the values in there with the number, a user constant of say 0 or some other number. Another way that we can handle missing values is by replacing the missing values with the mode or the mean. All right, so categorical variables, obviously we replace with a mode. Remember, the mode is the value that is the most frequent in that distribution. And so, for instance, this is a cylinders in the car. I might replace it with the most frequent value in there, which happens to be 4. All right. Or I can replace continuous values with the mean variable, the mean value. And so calculating the mean of the distribution of the values and then replacing it with that value. Oftentimes, replacing the mean in a mode will sometimes work well, but oftentimes if you have skewed data one direction or another, the mean is not always going to be the best typical value and can result in your confidence intervals being overconfident or over optimistic. Oftentimes it's helpful to consult domain experts in this or a database administrator to help understand the values that are missing and what best approach to take when dealing with these missing values. And then the third way is to replace those missing values with a random number or random value. We can take random values from an underlying distribution and then proportionally distribute those numbers to each of those fields. This is actually a superior method. There are a lot of different methods for dealing with this type of replacing missing values, and we'll talk about those in upcoming lectures. No matter what you do with handling missing data, you need to make sure that whatever you're doing, whatever values you're replacing it with, makes sense. All right. So even in this small data set of values related to cars, we could actually end up introducing data that has errors. All right. So if I replace, say, the cubic inches with 82 on a car that has 8 cylinders, all right, that's a pretty strange engine size. All right. And so we need to be careful on how we replace the variables that we're looking at replacing, and making sure that they make sense, because we don't want to introduce for sure any kind of misclassifications. And so improper use or improper handling of the pre-processing can introduce errors within our data set as well, such as misclassification. So look at this small data set, all right, where I have a lot of different countries here, and just the frequency distribution that shows 5 different classes: USA, France, US, Europe, and Japan. Well, I can easily look at this small data set and say, okay, well, there's only one instance of USA, all right, but there's 156 instances of US, all right. Obviously, USA needed to be put into the US category, all right. Just a small typo. Something may not be as identifiable is the fact that we have one instance of France, all right, but 46 instances of Europe. Obviously, France is in Europe and should have been categorized as Europe instead of as France, all right? And so these are just some misclassifications, probably some data entry errors or something like that, but we want to avoid this or kind of identify this when we're looking at our data sets and pre-processing them, and be consistent. When it comes to labeling and continuous variables, we want to make sure that we're consistent with our labeling of these classification variables. When we're looking at data sets, especially large data sets, we want to identify some outliers. Oftentimes, outliers can be really unique and help identify some really unique inferences about our data set. But these are values that lie near the extreme limits of our data range. Okay. Oftentimes, they can represent errors in our data as well. All right. And there are a lot of different statistical methods that are sensitive to outliers and actually may produce unstable results. So such things like k-means and neural networks are oftentimes very sensitive to outliers and therefore can become unstable. All right, so we need to make sure that we're handling those in very systematic ways, and we'll talk about normalizing data in just a bit. A couple of different ways to be able to identify outliers. One is a graphical method. All right, so everybody's done a histogram, I'm sure, that's taken this course, either in a college level statistics class or even maybe in high school. All right. But a histogram examines the values, especially in a continuous numeric field, all right, and can show outliers within that. And so if we're looking at the distribution of the values within a histogram, anything that is more extreme is going to come off as like a tail, all right, and we can quickly identify that visually and then do something about it. Scatter plots are also helpful in being able to identify outliers in a two-dimensional space, so across 2 different variables. And so here we see a scatter plot of the cars data set looking at the MPG versus the weights. And then we see 2 possible outliers that we need to handle. One where a car weighs 192.5 pounds, and then another one that gets over 500 miles per gallon. So two-dimensional scatter plots are helpful in identifying these outliers as well. Mathematically, we can also identify outliers by looking at the measure of the center or the spread of the data. And so when we're talking about measures of center, all right, or measures of location, we can do numerical summaries. We're looking at the mean, the median, all right. Those are measures of central tendencies or measures of center in our distribution of our data, all right. And so we can look at those as being able to look at the measure of center and spread and determine which are these are outliers. When we're looking about the spread of the data, we can look at the range, how far are the minimum and maximum values. We can also look at the variance or the standard deviation to look at the variance within that data set as well. All right, these are other ways to be able to look at that. So being able to mathematically look at the mean and the spread of the data is great for being able to identify different outliers. All right, data transformation has to deal with transforming your data into ranges that are more similar in size. Because many data mining algorithms, many of the models that we're going to look at later on, can be adversely affected by having differences in our variable range. For instance, here, look at the batting average of baseball players. All right, usually that's between 0 and 1. All right, with most batting averages probably being between 0 and 0.4. Very rarely do you get batting averages that are much higher than that. But if we look at the number of home runs, we can have anywhere from 0 to 70. All right, so the two ranges of those batting average and the number of home runs are much, much larger than one another. All right, so they have greater ranges, especially with the number of home runs. So that's going to have more influence on our data's model. And so therefore, these numeric fields would benefit from being normalized or doing a data transformation or the normalization of these variables or of their ranges. And so there are different ways to be able to scale these variables so that they're kind of on the same scale. All right. One is a min-max normalization, and this is just the mathematical breakdown of this. But in this, all of our variables should be scaled down no matter what the values are between 0 and 1. All right, so we look at the minimum value, we look at the maximum value. All right, and we can get everything, we can scale all of those down between the values of 0 and 1, where the lightest, this is doing it on the weight of these vehicles. So the lightest vehicle would be at 0, all right, and the heaviest vehicle would be at 1. And if they're nominally distributed, all right, that means that the one that is about the average or value should be somewhere around 0.5. Another way to do standardization is using a z-score standardization. And this works by taking the difference between the field value and the mean value. All right, and so this scaling is a little bit different, and it uses the standard deviation of the values as opposed to just the minimum and maximum values. And so here we see an example of taking the weighting, and everything should be centered around 0, and we'll have negative values, have positive values as well. Decimal scaling is another way that you can normalize the values. All the values should be between -1 and 1. Here's the generalized equation for doing decimal scaling. The D represents the number of digits in the data value with the largest absolute value. All right, and so with the largest value for our weighting here is 4,997. That has 4 digits in it, so D is going to equal 4 in this particular case. And so the decimal scaling for these values, where you have the minimum value is the minimum value over 10 raised to the D. All right, in this case 4 is the number of absolute decimal or digits that we have, and so that ends up being 0.1613, and the maximum ends up being the maximum value, all right, with 4 digits, so 0.4997. All right. There are also transformations to be able to achieve normality. All right, this is talking about the skewness of our data. So we know that a nominal distribution of is commonly known as a bell curve, and that should be symmetric and centered around 0. All right, which means that we're centered around the mean, all right, or mu, and then it has a spread that's determined by the standard deviation. All right, and so on this scale, we see the nominal distribution is centered around 0, standard deviation of 1, all right? And that's known as a standard nominal distribution. There are transformations to be able to achieve normality, because most of the data sets that we're going to be dealing with are not going to be this beautiful bell curve and they'll be nominally distributed around the mean, all right? Most of the time, we're going to be dealing with skewed data, all right? And so there are a couple different ways to be able to measure skewness, all right? And that this is just one equation here that the textbooks give us, but there's a lot of different ways to be able to measure the skewness of our data, whether it's left skewed or right skewed. All right, we want to try to make our data more nominally distributed, because that symmetry in our data set oftentimes gives us better results when we're doing a lot of different statistical modeling. And so there are a couple ways to deal with skewness. We can apply these different transformation methods to our columns. So you have to do this by variable. All right. So where you can multiply by the natural log. All right. Or you can multiply by or take the square root of it, or 1 over the square root. So these are just some of the ways of being able to deal with skewness to try to make that data more nominally distributed. You can also graphically look at this by looking at a nominal probability plot. And so these are often done to try to get a visual representation of the distribution of the data set. And so if you end up with a data set that is very S-shaped, like you see on the screen on the left, all right, here, all right, that means that the data set is oftentimes skewed one way, either towards the lower values or towards the upper values, all right, depending on the data set. If it is nominally distributed, you'll end up with this nice linear graph where all of your data points kind of fall in a deviation standard here, all right. And so no matter what you do, you may want to do, and nothing says you have to use the same standardization or the same transformation for each one of your variables. You can use different ones. You use 1 over the square root for one column, or the square root for another column, whichever gives you the best results. But no matter what you do, when you're done with your analysis, don't forget to de-transform your data by using the anti of whatever formula you used. All right. This talks about the different z-score methods for identifying outliers. There's a couple of different ways for doing this as well. This is another numerical method for identifying outliers. One way is to look at the interquartile range. All right. And so if you think about quantiles or quartiles in this instance, the interquartile range is defined as the first quartile, which is the first 25% of the data. The second quartile is the 50th percentile of the data, all right, which also will contain our median. And then the third quantile is the 75% of the data. And so we can actually calculate the interquartile range by subtracting the quartile 3 minus quartile 1. And then giving us the spread of the first middle 50% of the data, all right? And then what we determine is we take that number, multiply it by 1.5, all right? And then anything that is above 1.5 times the interquartile range is considered an outlier, all right? Or anything below, so these are usually positive or negative, right? Or anything below 1.5, the interquartile range, is also considered an outlier as well. All right.